So this next one's a little bit sci-fi. Um, People like to ignore and discount technology that's only 10 or 15 years away as if it's impossible. If you took your phone today back to 1980, they'd be like, that's alien technology. That's impossible. So this is another one that it's within reach. So you should probably think about how old you're going to be in 10 or 15 years because you'll probably live to see this. Um, and this is about getting into space cheaper, faster, higher volume, and what we do in space. So there's a couple different parts here, and it gets a little complicated. Trigger warning. So we've had rockets for a while because it was a pretty simple way to do things. Even with basic engineering, simple tools, we were able to make rockets. It's the lowest budget of all the space launch technologies. But there's a better one, and it's called a coil gun. And the way it works is there's a coil, makes a tube, and you shock it with electricity. And when that electricity travels in a circle down that coil, it creates a magnetic field going straight down the tube. So if you have a launch vehicle that's coated in iron, thick layer of iron, then the magnetic field pulls it forward. And you have stages. There's the first stage of coil that lights up, pushes the pod forward. And then the next coil in the chain down the tube is going to light up, create another magnetic field that's further forward, pushes the pod forward, and it accelerates a lot. So coil guns, there's designs that you can do when it's when you want high efficiency. You can look at NASA's quench gun, which they were considering using on the moon because it uses a superconducting coil and the electric fields, the electric flow echoes down the tube, so you get to reuse the same electricity. But most of the coil gun designs have been really over-engineered, and so they're prohibitively expensive, and so we didn't do them. So where I came in is I said, let's make them cheaper. What's the cheapest way to make a coil gun? And usually the way that happens is find a way to mass produce them. So the way to do that is you've got a railroad that you lay a track north south. You're going to many rails in parallel. This is a very wide railroad. And then off of that, you're going to have east-west rails at intervals. You got another east-west railroad going. And they're each going to go about 60 miles. And there's a great spot that's nice and flat in the middle of New Mexico, not far from Roswell, actually, that can head up into the mountain ranges. It's a nice, gentle slope toward the mountains. And so once you have that line of rails, you put a really big rail car on it. This rail car is an entire factory. Like I said, there's many rails. It's a big railroad. That factory is going to have injection foam. So spraying foam, and it hardens. And the foam is going through an extruder to come out like cheese whiz in the shape of a hollow tube. And as it's pushed out, there's rail cars underneath that carry it along the east-west rail. So you're just cheese whizzing. It's like a giant macaroni machine. Cheese whizzing this foam that hardens in a tube, and you're carrying it all the way out. That allows you to continuously produce an entire coil for a coil gun, 60 miles long. Now, as this foam is being squirted out and foaming up and hardening, you are laying the coil into the foam. That saves you a lot of time and labor and expense. And the coil is not going to be a thick rod of copper. It's actually a hollow tube. And you're going to fill that hollow tube with conductive fluid. The conductive fluid is going to allow a lightning bolt to travel through that coil, for that segment of the coil. but it's going to heat the fluid. The electrical resistance of the fluid means it absorbs heat. So you have a little release valve. As the fluid gets hot, some of it boils and goes out the release valve. And then you can condense it and pour it back in. So that makes it hyper resilient, and it also avoids the incredible high cost of making that much copper for that long of a tube. It's a hollow casing insulated with a release valve and a condenser. The way you power it, the source of the power doesn't really matter. I mean, it does matter for climate and other things and all the other issues, but you could use wind, you could use solar, you could use nuclear if you want. You could even use coal-fired power plants. The source of the power isn't the issue. It's how you hold the power once you've generated it. So it's really popular to look at lithium-ion batteries, but those are expensive, and you can't mass produce enough of them for a coil. So what you do instead is you blow a glass container, thin glass shell, and it's empty inside. And you're going to want to heat this glass in an oven and then dunk it in a fluid of potassium solution. You could use just wood ash and urine if you wanted, and that'll hold the potassium ions from the wood ash, and the potassium ions penetrate the surface of the glass. And that's the recipe for bulletproof glass. It's that simple. So you make the glass container bulletproof. Now it's pretty strong. And then you're going to pump all the air out. So it's a vacuum inside. There's no gas. And you lay little strips of metal barriers, and that's called a vacuum capacitor. Capacitors are like a battery in that they hold electrons, but they hold it at a very high voltage, like a lightning bolt, and they don't hold a lot. Battery will hold more electrons at a lower voltage. And capacitors can release that electricity very quickly, which is what you need for the coil on your coil gun. And so by using vacuum capacitors and conductive fluid, you avoid the main expenses of electronic control systems, switches, capital components for your coil gun. This cuts out most of the cost. And you want to make these vacuum capacitors as big as possible. And the reason you want them as big as physically possible is because in a normal battery or capacitor, its amount of charge that it can store depends on its total volume. If you double the volume of a battery or capacitor, it holds twice as many electrons. Vacuum capacitors are different because the vacuum capacitor only has a mass of the shell. You just got a container of glass, and then the volume is empty. So if you make a vacuum capacitor much bigger, you make it twice as big in every direction, you're only using 4 times as much surface area for the materials, but you have 8 times the volume. So making a bigger vacuum capacitor gets better and better in terms of its efficiency at holding electrons per dollar of material. So you've got these giant vacuum capacitors. They'd be rounded over cubes, basically squircles, and you're just stacking them next to your foam coil. And then you have your power system above it, whether it's solar, wind, or whatever. So now you can have a launch vehicle of a few tons travel down a tube, and the tube is going to have to release the launch vehicle above most of our atmosphere, which is the tricky part. So the tube has to be lifted at the very end. The tube's going to be running for 60 miles, but then the last few miles it goes up at an angle. And the way you do that is you have tethers. I recommend using S-glass, which stands for strength. And S-glass is a third the weight of steel, but it's as strong as piano wire. And you can mass produce it a lot easier because it's just glass instead of iron. So S-glass tethers, and then above holding it up, the thing that's pulling it into the sky, is more tethers coming down on both sides. And those tethers have a clothesline that has a bunch of blimps. And the blimps material is pretty cheap. The main issue for blimps is keeping them inflated and replacing them if they're damaged. So keeping them inflated, we can do that better now because graphene, the carbon black, which you can produce just by holding a metal plate over a candle. It's the carbon black is the India ink. If you coat the inside of a blimp skin with carbon black, then hydrogen can't escape. And hydrogen is very buoyant, and we can produce a lot of it. We're limited on how much helium we can produce because we have to extract it from the ground. But hydrogen is just from splitting water. So we can produce lots of hydrogen, fill these blimps. No one's living in the blimp, so if it lit on fire for some reason, it's fine. Just haul it down the clothesline or replace it. And the hydrogen doesn't leak out. So now we can keep the blimps filled and use the clothesline to replace any damaged blimps. And there's hyper redundancy. There's literally thousands of blimps on these hundreds of clotheslines, lifting the tube of foam into the sky a number of miles. So once the launch vessel exits, it's going to fly out above the Earth. And you could use a rocket on the back to get that last little oomph. You would only need a tiny amount of rocket fuel because almost all the rocket fuel in the SpaceX and other launch vehicles, almost all of that is just to get the rocket up into the sky. Only a tiny portion of the rocket fuel is actually used to start traveling around the Earth or travel to other locations. So you'd only need a tiny amount of rocket fuel, if any at all. And once you've made this structure, you can just keep launching. You can launch a couple times a minute. And that would allow you, with just one coil gun, to launch hundreds of times more payload than Elon ever could. We're talking millions of tons per year from one coil. And the launch cost would mostly be electricity. And it's a much more efficient conversion from electricity to thrust compared to a rocket. So you could expect launch costs to be dozens, if not hundreds of times cheaper, depending on the cost of the railroad factory and other components. So that would allow us to launch a huge amount of material in space with just one coil. And then that factory on rails rolls north and starts making another coil. And then it rolls north and makes another coil. And then it rolls north and makes another coil. And you're probably going to want to make a few hundred of these. Plan for a few hundred at least. And the reason you want so much launch capacity, this is critical, is because when we start mining asteroids, which is going to happen, it's not a never. When we start mining asteroids, it's going to be with robots. You're definitely not going to have people up there. And the robots' big components, their structure, can be made out of the materials that we get from the asteroid. But there are certain components that, for a certain amount of time at least, will still be made on Earth. We won't have factories making computer chips in space at the same time that we've started robots mining in space. The robots start mining, and then many years later, we'll have built it out enough that we'll have computer chip fabrication there. So chips, sensors, and actuators will need to be launched into space to supply the growing number of robots. And the number of robots will grow very quickly. I wrote a few essays about this many years ago, The Imperatives of Space Industry and a few others, where I estimated the doubling time of robots mining in space. And it was funny because only a few months later, some academics and engineers published a paper saying the same thing. We can expect that once we have robots mining in space, then the total number of robots mining in space will be able to build themselves. You'll have factories. It's not nanobots. It's factories making components, assembling robots. They will double every 6 to 9 months. And a 6-month doubling means that in 5 years, there's 1,000 times as many. In 10 years, it's 1,000,000 times as many. And in 15 years, it's 1,000,000,000 times as many. So if robot mining starts out as just a few $1 million industry per year, then 15 years later, it's bigger by multiples than the entire economy of the Earth. So we're going to have a lot of robots on an exponential curve, and it's a fast exponential. Which means if you can't launch enough sensors, actuators, and chips, you plateau. You plateau at your sensor launch capabilities. So we're going to need the coil guns to keep that exponential growing. So whoever makes the coil guns cheaply and mass produces them can take the steepest exponential furthest, and they will dominate space industry. And I often hear this complaint, this false critique, going to the AI salon on space industry and all these other groups I try to talk to, where they claim that space industry won't grow beyond earthly demand, which is ridiculous. The space industry will be selling metals, precious metals, down to Earth to make cash revenue. But they're going to keep growing as fast as they can in order to capture market share. This is critical. This is how business actually works. So as soon as space mining robots drop gold and silver and platinum and vanadium and ytterbium on Earth, then all the miners on Earth go out of business because they can make it cheaper up there. And they want to keep growing for their own internal use in a space-based economy. Even if there's no people up there, they're going to want to have the most productive capacity. Because if your productive capacity is growing and your competitors isn't, then you own the future. Anytime someone wants to do something, they come to you. So it is about market share, regardless of the level of consumption on Earth. And so we can expect that space-based mining is going to grow rapidly. As soon as it starts, it's going to grow faster than any other industry ever has in all of human history. It's faster than AI, faster than a cell phone, faster than any app. It's going to be explosive. And it's going to be bigger than our entire earthly economy in less than 2 decades. And what we're going to build in space besides the mining robots, there's probably going to be a lot of compute. We're going to build a lot of computers up there. Not the ones Elon wants to do. He doesn't have good ideas. Instead, if you can shade an area in space, then the shaded area is able to drop in temperature down to the temperature of the ambient universe, which is just a few degrees Kelvin. It's really cold. Once it falls down to that temperature, you can operate superconducting circuits. So Dudley Buck was a guy in the 1950s who figured out how to use superconducting circuits to make transistors for computer chips. We didn't use them because we couldn't get things that cold. But in space, you can get that cold. And once things have gotten down to that low temperature, the computer chip runs about 1,000 times faster. So you don't need a lot of computer chips before the computer chips in space are more compute capacity than everything on Earth combined. So we're probably going to build a lot of superconducting chips, cryotronics, in space. And the specific type of cryotronic is likely to be what's called a Josephson junction ring resonator. It's just a horseshoe of metal laid on a thin surface. You can even do flexible adhesive plastic. And the echo of electricity in that horseshoe creates a magnetic field that'll hold information and act as a switch. So Josephson junction ring resonator cryotronics in space are what you should expect one of the main industries to be. And they'll be beaming data down to us and picking data back up. And all the processing happens up there. One of the other main things that they'll be building out in space is thin film mylar. Mylar is the like fire blankets, the emergency disaster blankets people give you, where it's a thin layer of plastic coated with a reflective metal. It's ultra light, and the metal is reflective. We will be reflecting sunlight using mylar and beaming it to other locations as our power distribution. Other people have talked about using photovoltaic, which is the solar panels, to collect electricity from the sun, and then to use that electricity to power microwave satellites that beam the microwaves down to Earth for earthly power generation. That's way too much equipment for the number of megawatts. You get this many megawatts, but you spend a lot of money on equipment. Mylar gets you the same number of megawatts where you want it with much less equipment, hundreds of times less mass, and thousands of times lower cost using abundant materials, which means you can scale faster. So, mylar reflectors are going to be the norm for transmitting power in space. One of the other things about the mylar is that when you beam it to the ground, it's just a hot spot. It's going to generate a region, probably a few miles across, where it gets really hot because there's lots of sunlight hitting from all directions, all these reflectors floating up in the sky. And we can use that heat to just power a heat pump. We can have a Stirling engine cycle on blackened ceramic tubes and generate electricity using minimal equipment costs. So we can roll out power generation in very remote areas where it's normally too expensive to build out. And one of the other things I want to mention is how we're going to be mining in space. There's lots of cute comic book versions of how mining happens in space, but there's actually engineering about how you want to do it. When you have those mylar reflectors all beaming to one spot, you can get that spot up to a decent fraction of the temperature of the sun, which is enough to turn rock and metal into a gas. It gets so hot it actually boils. And then you're going to vacuum that hot gas of rock through a tube. It's going to be a really big tube, but it's covered in foamed glass. So you got a foam glass tube, it's pumice, and it's going to have a glass sheath running down it. You could slide the sheath out of the tube. And the pumice is going to have a gradient of thickness as an insulator, so that as the gas travels through, it only cools down a little bit, and then it cools down faster, and it cools down faster and faster and faster by the time you get to the end. And what's going to happen is as the gas travels down that tube, each different element, each of the elements on the periodic table is going to touch that glass, cool down, and lay itself down as a layer. Each different element at a different distance down the tube. So you're going to have a layer first where it's things like tungsten and bismuth, because they're the highest temperature refractory elements. And then as you get further down the tube, eventually near the end, you're going to get things like gold and aluminum, which have a much lower boiling point. So the whole tube gets covered in each separate element in a series based on its boiling temperature. And now you slide that sheath out and you can cut it apart, and now you can process each of those elements. And that's the lowest equipment cost with the lowest complexity. And because it's all glass, most of the material up in space is silicon dioxide. Most of it's glass. So you already have the material there. If you try to make any factory or equipment in space using anything other than glass, you are taking away from your exports. If you want to make something in space using nickel, you would actually prefer to sell the nickel to Earth. So it's better to build everything that you can in space out of glass. And there's also going to be a surplus of raw iron. Glass and iron are going to be the main materials for almost everything in space. And that rate of cycling that you can have means there's a huge throughput of material, a huge scaling potential. There's so much room in space with all the mylar reflectors. You're going to be able to process whole asteroids very quickly. You just blow it up inside a balloon. You're detonating it inside a big container of fabric, and you catch all the pieces and put the chunks in front of the sunlight, and they boil, and then they condense on the inside of the tube. So if you look at that doubling time, if we're doubling every 6 months, it's not going to take long before we've eaten up all the asteroids in the entire solar system. The entire asteroid belt is only a few percentage the mass of our moon. And we're definitely not going to eat the moon, because that would get rid of tidal action. It would basically destroy most coastal environments. We got to keep the moon and the Earth and the sun. But if I had to bet on it, everything else is up for grab. Mars is the most depleted of all the terrestrial bodies in the solar system. There is less valuable stuff on Mars than anywhere else. So no one's going to be living on Mars because they won't have any valuable exports to pay for living there. It's not worth it. And so after the asteroids get eaten up, we're going to be looking for where's the highest value to mine after the asteroids. And that's the planet Mercury, the one closest to the sun. It's a little bit bigger, more massive than our moon, but it's 80% metal rich magma. So we just crack the surface, drill down, lay a few nukes, crack the surface. Magma flows out with a very high concentration of metal in it. And it's that high percentage of metal, which means it's efficient to process. You're not spending a lot of time, resources, or equipment costs to get a lot of metal. And the metals that are in Mercury are all the precious metals. I'm not talking just gold and silver. I'm saying all the metals that we use for electronics, all the metals that we use to dope lenses for different kinds of lens effects, all the catalytic metals for different chemistries. Basically, everything you need for technology is Mercury. The planet Mercury has about 80% of the entire solar system's recoverable tech metals. So whoever owns Mercury owns the future. And you're going to want to make a foam coil gun to get there.